In this video, I want to discuss just a couple other little details of Newton's laws that pertain to orbits. And one of them is the simple fact that when two objects are gravitationally interacting, namely in an orbital situation, they don't orbit each, one object really doesn't orbit the other. Okay? They orbit what's called their common center of mass. So if we have mass 1 and mass 2, it's not like if this one is a little smaller than this one, the first one, that the second one orbits around the first one. You could say they both orbit each other, but more precisely, they orbit about their center of mass, which is like the pivot point where a teeter-totter is balanced. So two equal weights will pivot right in the center, and that's actually the point that both of these stars, in this case, we're considering them stars because in a practical sense, stars exist in binary systems. They both orbit this point here. Now, if you increase mass, twice the mass, 1 times the mass, then that pivot point just shifts over to the larger mass, etc. When you have a star and a planet, like our star, the Sun, and a planet, Earth, then the pivot point is extremely close to the center of the parent star. So this, in planetary systems, this idea doesn't really matter very much, like in our solar system. However, and shortly we're going to be analyzing the physics of binary star systems, in which case we're going to have to understand and apply the principle where that pivot point or center of mass shifts appreciably far away from the center of one particular star. Okay. Because the planets, well, they're much less than 1% of the mass of the whole solar system, in the case of our solar system. And in fact, it's because of that they orbit center of mass, even with planetary systems. The parent star actually orbits this point, so it wobbles around that point a little bit, and that's a means by which the existence of extrasolar planets is discovered using the Doppler shift of the sun, the star, wobbling back and forth. The other thing I want to mention is there's a comment on orbital energy, and it stays constant. Now, even though we haven't had our unit on energy yet, we have something called energy of motion or kinetic and energy of position or potential. So here is a planet a long ways away from the sun. It's got a lot of potential energy, and it's also moving pretty slow, which means it has less kinetic energy. More potential, less kinetic. And as it zooms by close to the sun, it's given up a lot of its potential energy, and it's now gone to kinetic, and it's moving faster. We'll get more into the details of that when we discuss energy particularly. And then an interesting phenomena that is not all that rare is a comet on a hyperbolic orbit comes into our solar system and zips out, probably coming from a region in the outskirts of the solar system called the Oort cloud, a gravitational disturbance, and it comes in on a one-time trip around the sun. Now, that's pretty common, but occasionally that comet might enter the solar system in a fairly close proximity to Jupiter, and Jupiter's gravitational influence might swing it around like this, which puts it in an opposing orbit around the sun, really slowed it down and got it under control. So now it's a bound orbit. So it went from an unbound hyperbolic to a bound elliptical because of Jupiter's influence. And Jupiter says, I don't care. Doesn't affect me at all. Actually, the comet affects Jupiter ever so slightly, but Jupiter is so massive that it's essentially unperturbed. So the comet goes from unbound to bound, and some of the comets that we currently have that repeat their orbits in our solar system originally were on hyperbolic paths, and now they're on bound elliptical paths. And now let me discuss gravitational fields in brief. So we have two objects interacting. We have the Earth and the Moon in this case. And I'm showing the separation distances r. Basically, that's like the orbital radius of the Moon, we can think of it as. Don't worry about the center mass issue, which also actually does come into play because the center mass of the Earth-Moon system is somewhere under the crust of the Earth. But in any case, think of it as the distance between the center masses. And mg little m is mass of the Earth times the g field produced by the Moon, little m. And this force, mg, which again is just gravitational tug or weight, is the mass of the Moon in the gravitational field of the large mass, the Earth. So with that as definitions, Fg equals mg. We've seen that before, and now we know the universal law of gravity. G big M, little m over r squared. Little m's go away, and so we can get the gravitational field as follows. G equals big G big M over r squared. This is the gravitational field strength of a mass m a distance r away. So that's the G field of m at r. And that exists whether or not the, notice the little m goes away, so it's not necessary. This mass can be gone, and the G field of big M is still felt out here. If there's nothing to act on it, if there's nothing for it to act on, then nothing happens. But nevertheless, it's there. Okay. So this is a statement of equivalence with Newton's third law, action-reaction. The force of big M on little m has to be equal and opposite to the force of little m on big M, Newton's third. Therefore, we can say that the weight of the Moon, from the point of view of Earth, that's the gravitational tug of Earth on the Moon, is equal to the force trying to connect these two. You could say the force of the Moon on Earth, but that's encompassed in this. Little m goes away, and we have the gravitational field of big M, G big M over r squared. Same thing as we already had. But equivalently, we can switch this around and say big M, G of little m. So the Earth's mass in the G field of the Moon is equal to that same gravitational tug. But big M divides out, and we get the G field of the Moon, or of little m. So same form. So you see the equivalency there, and hopefully that's pretty straightforward. Now, the resulting gravitational field, it's an inverse square law, and so this and this little graphic indicates the relative strengths of the G field, drawn in the form of what's called a vector field. So think of this as in three-dimensional space, and at any point in space, you have a little vector pointing to the center of mass of the object. So think of this as being in three-dimensional space. Now, if we just simply observe the gravitational field on the surface of the Earth, for all practical purposes, it's uniform, and so the vector lengths are the same, and moreover, they're essentially parallel. But precisely, these lines are going toward the center of the Earth, so there's a little bit of divergence, a little wider up here than down here, but ever so slightly. A couple other characteristics of the G field and how we graphically depict them. This kind of shows the whole thing. So it can be, the field can be characterized by what we call these lines of force, which point in the direction of the force on a mass in that field. So if we put a mass here and observe the force acting on it, well then that direction is given by the vectors. So maybe it's good to look back here again. This represents the force on a given mass, a unit mass, in this location. Moreover, the relative spacing between the lines indicates the strength of the field, so it's greater here than out here, and it's even more the closer we get to the Earth. And actually, you can imagine these things converging down here. So if we had this thing compressed to a point, that those lines would become infinitesimally close together as the gravitational field approaches infinity. All right, of course we'd have a black hole then, and we're not going to get that out of the Earth, but theoretically that's what would happen. So the relative spacing indicates the strength of the G field. Moreover, the concentric lines, those red lines, are regions of uniform strength of the gravitational field. There they are. This red line, this one, marks out a boundary where the field strength is the same. And the spacing between these, what this is also illustrating is the relative amount of difference or increase, the way I'm going here, in G field strength is showing the inverse square law, namely that there's equal quantities of G field difference here. Like say, let's just assume for as an illustration that it's 10 meters per second squared here. Well, maybe there's 5 between here and here, so this would be, I'm sorry, so maybe it's lost a couple. So this is 8 here, and then you go here and maybe it's lost a couple more. It's now 6 meters per second squared, 4 meters per second squared, 2 meters per second squared here. So in other words, the amount of difference in G field strength is constant between these lines. And because of the inverse square law, the spacing between the lines increasingly increases compared to the previous. Hopefully that made sense. So that's just a brief introduction to gravitational fields, and hopefully that increased your understanding a little bit. We'll catch you next